where we cut through the noise, grab the essential insights from a stack of sources, and deliver them straight to you.
Think of this as getting the aha moments from cutting-edge research without having to wade through pages and pages of equations.
And today, we are doing exactly that. We're tackling a recent research paper from ArcSieve that's, well, it's really pushing the boundaries on a fundamental problem in AI.
Which is?
Getting models to truly understand and remember information over very, very long sequences. Think huge documents, entire books, long conversations.
Right. So our mission today is to break down why this is so tough for current models, even the really powerful ones you hear about, like transformers.
And then explain the clever new ideas this paper introduces. They're aiming to build AI that can actually handle, massive amounts of information spread out over time.
And we're going to focus particularly on the core academic insights here, the innovations that make this work significant from a research perspective.
Exactly. Our goal is to give you a clear shortcut, a real understanding of these complex ideas, straight from the source material you shared. Ready to dive in?
Let's do it.
Okay, so first, let's set the stage. What's the challenge? A lot of modern AI, especially language stuff, relies heavily on attention mechanisms.
Right. Things like the attention in transformers. And they are incredibly powerful, especially for retrieving relevant information without a certain context.
How do they work, basically?
At their core, you can think of them like a really sophisticated associative memory. They learn to map information, bits, keys, and values.
Okay.
Then, when you give the model a query, like a question or the current word is processing, it compares that query to all the stored keys.
Uh-huh.
And based on how well they match, it retrieves the corresponding values. It's like having a dynamic index for everything the model has seen in that context.
But the standard way it does this involves comparing every single piece of information, every token.
To every other token in the sequence. Exactly.
And that's the bottleneck, right? Especially for long sequences.
That's the crux of it. If your sequence gets twice as long, the computation, the memory needed, it doesn't just double, it goes up by a factor of 4 quadratically.
Oof.
Yeah. Make the text 10 times longer, you need 100 times the resources. This quadratic scaling basically puts a hard limit on how long a context-standard attention models can realistically handle. They just run out of steam.
And the paper we're looking at frames this problem really nicely, thinking about these models through the lens of associative memory.
They view it as a system, learning this key value mapping, driven by an objective related to, say, how surprising or informative new input is. And there's sort of two optimization loops happening.
Two loops.
Yeah, an inner loop that's just focused on optimizing the memory parameters themselves, figuring out the best key value associations,
Okay.
and an outer loop that optimizes everything else in the model around that memory component.
Got it. So, using this memory perspective, what are the specific shortcomings the paper identifies in, well, most of the other recent models trying to tackle long sequences, particularly recurrent ones?
They point out a few key things. First is the online nature of memory updates. Many models update their memory based only on the single current token they're processing.
So they just see one word at a time.
And they try to update their entire memory based just on that word, while kind of holding on to a compressed summary of the past.
It sounds like trying to memorize a lecture by only focusing intensely on the last word the professor said.
Exactly. You end up greedily stuffing that single token into memory, potentially missing how it connects to the broader paragraph or the overall argument. You memorize tokens, not context.
Makes sense. What else?
A second big one is limited memory capacity. The actual architecture, the way the memory is built, constrains how many key value pairs it can reliably store and retrieve.
Like having too few index cards.
Kind of, especially for models based on similar linear structures or basic update rules like Hebbian learning. The paper points out, theoretically, that their capacity is often tied directly to the input dimension, which might not be enough for complex long-range dependencies.
Okay, limited capacity. And the third issue.
Less expressive memory management. How does the memory actually learn those key value mappings? Often it's just standard gradient descent acting on that inner loop.
And gradient descent isn't always the best.
Well, it relies only on the immediate slope first-order information. It can easily get stuck in suboptimal configurations like a shallow dip in the optimization landscape, rather than finding the best possible way to organize the memory. It leads to less effective key value mappings overall.
Okay, so we have these core problems. Attention scaling quadratically, other models struggling with context, limited memory storage, and maybe not the best ways to update that memory. How does this paper propose to fix this? What are the big ideas for building this long-term neural memory module?
They introduced several really interesting interconnected innovations. The first one tackles memory capacity head-on. They propose using higher-order feature mappings and also making the memory itself deep memory.
Higher order features. What does that mean in practice?
The intuition is to make the information fed into the memory, the keys and queries, much, much richer, instead of just using the raw input vectors.
Uh-huh.
They transform them using techniques inspired by polynomial kernels. Think about taking your input features and creating new features that are combinations like squaring them, multiplying different ones together, up to a certain degree p.
Ah, so you're not just feeding x and y, but maybe x, y, x squared, y squared, x, y. All those interactions go into the memory system.
Exactly, but across potentially thousands of dimensions. This massively blows up the effective dimensionality of the input that the memory sees.
And that helps capacity.
Hugely. The paper shows theoretically that this polynomial mapping can break that linear dependency we talked about earlier, boosting capacity significantly. It allows the memory to store much more complex relationships between inputs.
It's like giving the memory system more complex tools to work with the information.
Precisely. And they combine this with deep memory. Instead of a simple linear layer for the memory, they use a deeper network, like a multi-layer perceptron, MLP, often with residual connections.
And making the memory structure itself deeper also helps.
Yes, their theory shows that depth alone increases capacity beyond simple linear memory. So you get a double whammy, richer inputs, and a deeper storage structure.
And they connect this back to standard attention too, right?
They do. They note that these polynomial features can actually approximate the kind of exponential feature map used implicitly in softmax attention, which gives a nice theoretical justification. Plus, they interpret the learned coefficients of these polynomials as a kind of cading mechanism. The model learns which combinations are important.
Okay, that addresses capacity. What about the issue of just memorizing the last token versus understanding the context?
That brings us to innovation number 2, the sliding window update rule, which they specifically call the omega rule.
Right, because just using the current token is too narrow, and using the entire past is impossible.
Exactly. So the omega rule finds a middle ground. It's a recurrent approach where the memory update considers a window of the most recent tokens, say the last C tokens.
Okay, like sliding window attention does.
It uses a window, yes, but the crucial difference is how it uses it. The omega rule optimizes the memory's internal objective based on the sum of contributions from all the tokens within that window, not just the final one.
The sum of contributions, meaning it aggregates the surprise or relevance signal across the window.
Precisely. And there's another clever piece, a learned decay term, gamma.
Learned decay.
Yes. For each token within that window, the model learns a parameter that can scale down its contribution to the memory update. It essentially learns to prune or ignore less relevant tokens inside the window.
Ah, so the model itself decides which parts of the recent context are important for updating its memory right now.
Exactly. This makes it fundamentally different from, say, standard sliding window attention, which might just compute attention scores within the window. The omega rule is explicitly designed and optimized to build a memory representation of the context captured in that window, not just individual tokens.
Okay, richer features, deeper memory, and now this learned context window rule. What's the third piece?
The third major innovation is about better memory management, improving that inner loop optimization we talked about, going beyond gradient descent.
So improving how the memory tunes itself internally.
Exactly. The paper's most advanced model, called Atlas, incorporates a more sophisticated optimizer for updating the memory parameters. Specifically, it leverages an optimizer called Muon.
Yuan, what's special about it?
It approximates second-order information. Remember how gradient descent just knows the slope?
Right? First order.
Second-order methods also consider the curvature of the optimization landscape. It's like knowing not just which way is downhill, but also how steep the curve is, whether it's a narrow valley or a wide basin.
Which helps find better solutions.
Potentially, yes. It can help avoid getting stuck in port local minima and converge to more effective memory states. Using this kind of approximated second-order information for the internal memory update is a key theoretical advantage. And the paper notes Atlas is the first recurrent architecture that's also parallelizable to actually implement this.
That sounds like a significant technical step. Okay, these are three really solid technical pillars. Enhanced capacity, context-aware updates, and better internal optimization. How do they actually combine these in the models they built?
They present a sort of family of models. You have simpler ones like deep linear attention, DLA, which basically adds the deep memory concept to a linear attention baseline.
Just to test the deep memory idea?
Yeah. Then there's DeepTransformers, which they show as a strict generalization of standard transformers, incorporating deep memory and an approximation of the softmax kernel's features.
Okay, and then building on that.
You get DOT, which stands for deep omega transformers. That takes deep transformers and adds the crucial omega rule for that sliding window context memorization.
Makes sense. And OmegaNet?
OmegaNet combines the polynomial features for high capacity with the omega rule, but uses standard gradient descent for the memory update. It really focuses on that interaction between richer features and context window optimization.
Finally, the big one, Atlas.
Right. Atlas pulls everything together. It uses deep memory, either a standard MLP or a gated MLP in Atlas++, the rich polynomial or approximated exponential features, the omega rule for context, and the sophisticated muon optimizer for the internal memory updates.
So it's the full package.
It really is. And importantly, they designed it to be trainable in parallel chunks, which is critical for handling massive data sets and long sequences efficiently on modern hardware.
Wow, okay, so these architectures sound quite powerful conceptually, but the proof is in the pudding, right? How did they actually perform in experiments?
They ran a pretty comprehensive set of experiments: language modeling, common sense reasoning, tasks specifically designed to stress memory recall over long distances.
And the needle and haystack type tasks.
Yep, those two, where the model has to find one specific piece of info buried in a potentially huge document.
So what were the key takeaways? Did the innovations pay off?
Overall, yes, very consistently. On standard benchmarks like language modeling, the models incorporating deep memory, and especially the omega rule, like dotted DeepTransformers, showed clear improvements over strong baselines, including transformers enhanced with just deep memory.
Okay, so the omega rule adds real value.
It seems so. And models like OmegaNet and Atlas generally outperformed other recent efficient RNNs and local attention methods on these tasks.
Did they see the improved memory opacity you talked about?
Definitely. There are these synthetic benchmarks designed purely to test memorization ability, like MAD, Memory Augmented Decoder. Atlas achieved state-of-the-art results there, particularly showing it could handle complex memorization challenges better than competitors.
And the really long sequences, the millions of tokens.
That was another highlight. On benchmarks like BABILong, which go up to, 10 million tokens, Atlas scaled really well and outperformed other models specifically designed for ultra-long contexts. It showed it could push past the typical limitations.
What about retrieving specific facts from those long contexts, like the needle and haystack?
They performed strongly there too. On in-context recall tasks, Atlas and OmegaNet were competitive with standard transformers, which are good at recall within their context window, and significantly outperformed other state-of-the-art RNNs. This suggests their memory system is effective at storing and retrieving information accurately.
Any interesting findings from ablation studies? Taking pieces away?
Yeah, those were informative. They confirmed the importance of things like using a gated MLP for the deep memory, showing it was better than a plain MLP. They also found hybrid architectures combining features sometimes worked best.
Uh-huh.
And crucially, the benefits of polynomial features and deep memory seemed especially pronounced when combined with the omega rule. They work well together.
Synergy. What about that sliding window size for the omega rule? Did making it bigger always help?
Generally, yes, performance improved with a larger window size Cs. But the interesting part is why it scaled well. They attribute it to that learned gating parameter, gamma.
Ah, the pruning mechanism.
Exactly. Even with a large window, the model learns to downweight or ignore the irrelevant parts, focusing the memory update on what actually matters within that context. It's not just seeing more, it's learning what to focus on within that view.
That's smart. And overall scaling. Bigger models, more data.
They showed promising scaling results. As model size and context length increased, Atlas and OmegaNet generally achieved better performance, lower perplexity, compared to baseline models, suggesting the architecture is well suited for future large-scale AI development.
Okay, this has been a really fascinating deep dive. We went from the limitations of standard attention, that quadratic cost, and the challenges facing recurrent models in truly capturing long-range context.
Right, the issues of online updates, limited capacity, and basic memory management.
To these really quite sophisticated solutions focused on fundamentally improving the memory component.
Making it deeper, feeding it richer, higher order information, updating it based on a learned window of context, and even using advanced optimizers for its internal state.
It really reframes the problem around building a better, more capable associative memory within these large models.
Absolutely, it's a powerful lens to view sequence modeling through.
And it leaves us with a pretty interesting thought to chew on. We've seen how enhancing this artificial memory in specific, theoretically grounded ways unlocks performance on these really long sequences. So if you think about associative memory as this process of mapping queries to values, learning what's relevant, what's surprising, how might studying the way these models learn to filter context, especially with learned mechanisms like that gamma parameter in the omega rule, how might that give us insights into biological memory?
You mean how our own brains decide what's important to remember from the continuous stream of experience we encounter?
Yeah, Could understanding how Atlas learns to prune its context window teach us something about attention and memory consolidation in humans or animals?
That's a great question. What new connections between artificial and biological learning does this perspective open up? It certainly makes you think differently about how memory, context, and relevance interact.
Definitely something to ponder. Thanks for breaking that down.
My pleasure. Until the next deep dive.